of artificial intelligence. So again, we follow the same kind of approach. We'll talk about the motivation and then how we can do how we can develop the models and then some improvements, some mathematics, and then the case study. So if we talk about the traditional neural network, I've taken few picks from some uh, books and some blogs. So it's interesting to see here. You can see here initially we start with a perceptron. We have two input and then we connect it and take output. Consider yellow one as an input layer, and your orange is the output layer, and green as a hidden layer. And then comes the feed forward network. And then if we add a radial bias here, so these are known as radial bias functions, RBF. And then if we increase the layers, then we are moving towards a deep feed forward network. If we have some kind of a bypass, some kind of a back movement mechanism, we move towards recurrent neural network. And then if we in backward, if we put certain kind of gate function. Okay, so yeah, I'll let me take the laser pointer. So we put gates. So we put we move towards LSTM, and then we modify the gate mechanism and all that. We move towards GRUs, and then the topology is different. Now you can see here that hidden layer is less. So it's a way, and output and inputs are more. It's a autoencoder scheme, and then variational autoencoders, denoising autoencoders, then the sparse autoencoders, and then we have Markov chain, Hopfield network, Boltzmann machine, restricted machine, deep leaf network, and then deep convolution networks. Okay, deconvolution networks, and then deep convolution now and inverse graphic networks. All these networks are all around us, whether you talk about GN or LSM or ELM. But the something is very interesting. Something is very common everywhere, and you can see what is there. There are point which are processing point. There are corrections between the points there. So that's why they are called as the networks there. And that is one kind of a thought that how that can we use a different way of uh, doing it, or can we see it from a different perspective? This one is any of these networks which I have shown you. They have some kind of summing points. They have some connections between the two nodes, and there is some kind of a topological arrangements. And the thought is, can we visualize these things from a graph point of view? And that's how, and then can we solve it from the graphical perspectives? And these things exist because now I'm defending it from the perspective of graph networks there. Traditional networks, deep networks, we have a lot of things we have studied. There are a lot of applications. But when we talk about some kind of other arrangement, you'll or you visualize the things in different way, you'll find there is a graph. Like we can have a social graph. Okay, so you are working on whether you are using say any social media. So you have graphs, you as a person, and then this person is connected with another person, and then that is connected with another person, and likewise. Okay, and each person represents some kind of a data. We have a transportation graph, start point and the end point and the trajectory. We have brain graphs, so the neuron points and then how they are interconnected. We have web graphs. We are working in bioinformatics or biology, chemistry. Then we have molecules, and then molecules are connected with each other. In medicine, we have gene graphs. So you can see that we now what we are trying to visualize. We are trying to that data as a graph basically. Like this is a social graph, and now we can solve this problem in many ways. I want to know about any of these person. Say I want to know about anybody here, any points with this one. Okay, and I'm here. Okay, so I know what is my connection with this one, and this connection of this with this, and the connection here, and then the connection here, dependencies and connection, and finally I can figure it out what is the relation here. So this one is a social graph. You can say this can be a graph of friends and family, and then local area friends, and now they are, and we know that they are interconnected. So if we are at one point, we can reach to the another point of the whole structure. And that is one kind of a motivation of this kind of theory. This is another one which is more easy, you can understand. It's a traffic map. So we know the city, and at city we know that these are the paths, and there is a junction. So now if you put the city map like this, it's a graphical representation. We know that this is the center point where other paths are connected. So this one is basically a representation of node and branches and all these things. So we can visualize the traffic map as a graph net. Okay, as a graph. Similarly, in optimization also, we can treat these node points. This one is a TSP problem figure. So you can see these are the nodes, and then how the nodes they are connected with each other, so that we can get a minimum distance path. If we start from one point and reach to the same point after visiting each and every city. So they are, again we have end point and where we have connections. What I am to defend here is that the formulation of a problem from a different perspective, we can put the problem as a graphical problem. Like I take one case, this is medical diagnosis. Okay, so we have a phenotypic abnormality. So you can track it both ways. Okay, and then there can be three cases: neoplasm and abnormality of the face and abnormality of eye. And then abnormality of eye is again two different sections there, and likewise. And now if some case is here, then either you can put it like this way, that okay, if it is uh, amblyopia, so then what will happen? It reduce visual, it may create abnormality of vision here, and it can be connected, or it can be go other way around also. So if there is a arrow, it's a directed graph. If the arrow is not there, it's a non-directed graph. So you can, so now we have a different thought, and the thought is we can use these kind of directions and all these things to identify the diagnosis and all that. Same is in the drug discovery. We know that okay, this is one kind of a drug, and it is made of molecules. And in chemistry, we know that molecules, they are related with each other. They are combined with each other, some certain kind of bonds known as chemical bonds. And then from there, we can find out what are the effects and cause and effect. So, but the hypothesis is we can relate them in terms of graphical presentations. Like this is an example of a drug discovery, and that's how the drug discovery take a big change after the introduction of AI and machine learning. You can see the landscape. You can see the landscape and the time taken. Usually, it take a lot of time, but here we can make it. We can make it in a graphical representation. We have two medicine. One on here, another one is here, and then their side effects and their combination and the structure. Then we check the similarity between the two structures. We find out a similarity, and then we can find out the various issues, side effects, binding property, treatment properties, and lot and lot. It is being used in drug discovery. This is another example that is basically we have already seen the COVID spread. It's a graphical problem. You can take it that way. That okay, this is the person, and then who are the next three surrounding person, and who is the affected, and then where he has visited, and then it bring from here to here, and then how it spread, and then how it moves, and all those things. So what we are doing is, what we are trying to do here is we try to analyze the whole problem from a totally different perspective. Same is the recommender system. You face this thing day to day. You just go to any kind of app uh, uh, app there, and you just search one thing, and then it will recommend few of the other things based upon the connectivity. This one is a scene graph generation. So a scene is given to us, and then the algorithm identify objects. Okay, so if this is the scene, it will identify there is a face, there is a mountain, there is a man, and then find out the relation between them, and finally it come out with a with the sentence. So it can be either way. It can be from scene to it generated text that a man with a hat riding on a horse, or it can be other way around, that if you give the uh, text, then it will generate a scene for you. Okay, but obviously those part for scenes and all these things, you need other methods also. But the point is, uh, there is a strong connectivity between the landscapes. So important points there. So people do a lot of things. Not only this, but they do a lot of things, and we'll talk about what we can do. Okay, so about these different points there. One of them is link prediction. We'll come to that one. Okay, this one is another application, human object identification. So this, you just take it like this. How we also process it. Okay, so the face is there. So we have person. It identify there is a knife. Okay, it identify there is a floor. There is a table, and then you can see that it's leaking the knife. So then there is a bond between the person, knife, was, and then table, and then there is another kind of thing, and finally it come out with the depending upon what we are looking for, it come out with a sentence, or identification of the objects, or whatever you want to do it, then you can do it. But the idea here is there are node points and there are connection between those node points. Like this is the text classification. So we have written a text. I'll take it here. The text is written here. We find out the relations between them, these node points, and then we give them the weightage, and finally we come out with the final judgment, maybe in your relation for NLP, maybe your sentiment classifications, and whatever thing you want to do, you can do it from here. Some work which we have done is on the pose estimation. So we know that as a human, we can represent human like this. Okay, there are nodes. We know that there is a head, and then there are we have shoulders, and then there we have your ankle point, middle point, toe point, and then how these points are moving. Based upon that, we can find out, classify that what the activity this person is doing, whether running or sitting or jumping, and likewise. So this one is again, you can see here we have nodes and there are connections between them. We can use it in chip design, VLSI also, physics also, particle physics. Well, these are certain examples, like, okay, just to motivate why we are going for it, why it is important, and likewise. This is the ecosystem. If you want to work in this area, this will help you. So we have TensorFlow, PyTorch is there. There are some dedicated, already developed graph network packages. Basically, you can use that one. That is, one is graph neural network. Okay, spectral, you can use it. You can use TU dataset, that is graph learning. You can use Stanford packages also. PyTorch geometric package also. There are some packages which are already available for your programming or writing your codes and all that. So how it is working? So this is an image, and then we take this image as a basically this is a data. If I talk about CNN, but here we take it's an image as a graphical representation. So we are representing each data as a graph there. Okay, and then we try to find out the relations between them. Okay, There we can find out the relation between them. Okay, this representation you can go it. What you can do is you can divide this whole picture into some small segments, and each segment represent one point here, and then we can check it what is the relation between them, and then we develop a graph from here. A graph can be many. It can be a simple graph. Okay, it can be a weighted graph. That means the relation between this one and this one is high, the relation between this one and this one is low. It can be directed, that is basically directional. Okay, it can be temporal, it can be dynamic, heterogeneous, and there are many other modes of representation of a graph. But we can do a lot of things. So summarize the whole things that what the data we have, we represent in terms of graph formation and what it can do. It can do many things. So graph means we have links and we have nodes. So it will do the job of node classification. We'll come to that. What is node classification? It can go for link prediction. We can do community detection. We can do a graph generation also. And there are many more such applications. This is the pipeline system. We have started in original GNN proposed in 2005, and then later on some modifications came into picture. How they performed or how the modifications are people have developed, we will discuss in the coming slides there. So what is the node classification? So node classification is like this. I have this graph. Okay? I have this graph, and say these are, let's take these are the each node point. These are the human beings. So we are here and we have some connection with each other. Okay, and then there are some other one who are here, gray one, but we don't know their characteristics. Okay, so you can take it like, okay, right now in this course there are some who are from MNIT. There are few who are PhD scholars. There are few who are supervisors. There are few from other institute, and there are few from other places. So each one is having one characteristics, and they are interconnected. They are friends also. So we have some connection, and if say somebody else is also part of it, and we want to know that what are the characteristics, say in a simple case, which institute or which place it belongs. So then what we will do is we'll check that connection of that with the other one whose characteristics are known. And based upon those informations, we try to figure it out the characteristic of a person. So in pictorial form, you can take it. These gray are the points where we want to color them. So which color should be there, whether blue or orange? So if we are able to color them, that means we are able to find out their characteristic. This is known as a node classification. Okay, so that is one part of there. We work here, so we put it automatically learns the features and then the algorithm part. The feature engineering is not that much required. We'll talk about directed and non-directed. So this undirected and directed. So undirected is basically no direction. That means A and C, the dependencies are same. Directed means A is directed to B. Maybe B is not directed back. In similar like in Twitter, it's not necessary that reverse direction is there. It may be a single directed one. Complete means every node is connected with every node. So these are the graphical representations. So a simple graph is like this. We represent a graph by V vertices, okay, and the edges. So we have vertices and then we have edges there, and how they are connected. So graph is basically G. It's a representation of vertices and edges, or you can say nodes and the connections, one and same thing. And mathematically we represent this picture because when you are going to write down a code, you are not going to draw these drawings there. So how we represent it? We represent it by adjacency matrix. So if there is a connection, it will be 1. If there is no connection, then it will be 0. That is how we can represent it. So the whole calculation which works further is in terms of a matrix. Okay. and then each node is having features. So these are the features of each node. This one is say myself, so I have certain features. This one is Mr. A has features, Mr. B has certain features. So now it's a representation of the data. So we have a representation of adjacency matrix which give us the idea about the network and how the connections are there, and then each node here is having certain level of features. That is basically, you can understand it from here. And then if new feature appear, then it has to propagate, and then what that we need to see that how it propagate and how it can be connected. So what is node level prediction? Again, I repeat it. Node level is basically we know that this is the connection. We want to find out the features of this one. Then this is basically node level uh, uh, detection, because we want to find out whether this person smoke or don't smoke. Okay, so this one is unlabeled node. We label it. The second category is basically link prediction. That is basically, is there any connection between this and this? Try to understand in this case. In this case, this link is there, already there. We don't know who is this person, and if we want to predict its characteristic, it's a node prediction. But once, if I know this link, I know the characteristic, I want to find out, is there any relation between this and this? This is basically known as edge prediction. And the another category is basically, I have one graph and there is another graph. I want to see how much is the similarity between those two. So that is the graph level prediction. So these are the three common things which we do in GNN. Okay, so node level, edge level, and at the graph level. And then we can use all kind of neural networks and all that. So we have discussed CNN, and there are challenges in CNN, and people comment on that. This is better than CNN graph neural network. Well, why and how? Let's see it. Okay, so this is the first thing. In CNN, if I'm developing a model, this size and the shape has to be fixed. So you have to do that pre-processing. Okay, this is independent of it. We don't need any kind of doing those things there. But the next thing is very exciting, and that is this one. Well, we know this is cat. This is, so this one is a size independent. But the point here is, if I train the network on this figure like this, and then I pass figure image like this, try to understand it. I have trained a neural network for CNN with this kind of a structure, and then I send the image, which is the same image, but it is just in opposite. You'll find that your model may not able to give you correct answer. And here, this is independent. So that's a good part with graph, that is isomorphism. Those things are eliminated. So this one is a good part. In CNN, my grid structure is fixed, it's hardly tight, fixed, constant. Whereas in graph, my structure is not very fixed. It has flexibility. In grid structure, the distances and all these things, they are fixed, constant. There's a strong relation between pixel here and pixel here and the arrangement. But in this one, we have flexibility. So we have three major differences, and that's why people attracted towards this domain and try to implement all these things. Okay, so this will work, and the question is then how the things will work. And let's take this slide. So what I'm doing here is graph knowledge. Yes. So this is the start point here. How the things will work. How this network is stabilized. How it will learn. Okay. So we know the property here. Okay. And we know the connection. We need to try to find it out. Or somebody new join us. Then how this thing is how that is shared, how that those features are shared. And this is, I take it a theory of gossips. How it will work is like this. So if this one is here and it has certain features, say y. So what will happen in next round? Okay, just okay. I'll come to those slides. I think those slides will come later. Let's discuss these things, then I'll explain those part which I'm trying to propose. So this one is a CNN picture. You can see here there is a strong binding, and the location of this point is very important. Whereas in your graph networks, this is flexible. There is no more important like this point has to be there. The important is the connection between them, and if the connections are maintained, it's okay. And why these connections are important? This help in message passing. That's why I was talking about the gossip sharing. Okay, so how it will work, and we can check it from this one. So what is message passing? How it will occur? So you can see here we have different nodes with different features. Some has green features, blue, and the red feature. What will happen is they will share the features. Okay, so second will share a feature with first, third will also share, and fourth will also share. And after the sharing of features, then one will modify the information. Okay, and it will modify as depending upon the connections which they have, and it will update the information here, and then it will share with the others, and then they will update. Okay, the updation and the sharing is a part. So now you can see what is happening at one has its own information, feature information. It will receive some from 4, some feature information from 3, some from 2, and now it has 2 sets, own and the shared one. Based upon that, it will update its own information system. Okay, so the simple one, which is one of the approach, it aggregate what is coming from the others. Okay, and then after aggregation, what it will do, it will update. So now what one is having the information of self along with the dominated information or some weighted information from others, like x1, if there is some information from x2, x3's own information, some information from some other, and likewise. This is how it updates its on information base. Okay, so this is how it is actually happening here. Every time it will do aggregation, and then it will do some kind of a updation. Okay, so that is basically scaling up and scaling down, and aggregation will occur because next, after some time, what will happen? In first iteration, 5 will share with 4, and then in the next round, so when 5 will share with 4, the 4 information here, that will have some uh, brown part here. In next round, then 4 will share the information with 1, and then after some time, depending upon the strength, importance, that brown part will reaches to 1. That is how the information exchange take place every time, layer by layer, and all these things. Okay, so those things I think you are clear. I'll take it another representation. So you can see here we have this aggregation. This is far away. We have some information. We update one, and after that we update the another one. This tree keep on increasing, and our network keep on learning. This is how the network learn from each other. So the two processes will occur. We aggregate. Now, how we do the aggregations and all those things, will come to that. Those are the variants or variations in the graph neural network, but we update the aggregations from the other, and then the aggregated information and the current information we use to update the information at any particular node. That is how it is being done. Now there are various ways. Aggregation, you can do it by mean. What you can do is, okay, there are 4 inputs coming from different 4 nodes which are connected. So you take mean of that. The another way of aggregation is you just take max of it. The another way of doing the aggregation is you use neural network there. So another way of using the aggregation is you use recurrent network. You can use any method here to aggregate it. And similarly for update, you can use mean. That means you take the mean of the informations which are coming from near around, and then you have your own, and then take further mean of it to update. Or you can take mean here and then this max of these two values. Or you can use a neural network here, you can use another neural network here to update it, and likewise. So these are the two functions where people keep on changing and developing new variants of it. So say this one is one. This one was proposed in 2016 by Kirf, very popular one, GCN, Graph Convolution Network. So you can see here how they are updating it. So they are updating as a sum of the normalized neighbor. So neighbor information, they take sum of it and they take normalization of it, pass through a nonlinear function. This is the aggregation technique they have adopted. In another one, which was multi-layer perceptron, so what they have taken is they have used MLP to aggregate the information from others. Okay. Then another comes is basically graph attention networks in 2017. So what they have done is they have taken the weighted attention. So they have put attention over the information and put a weight over it, and based upon these are just aggregation part I'm talking about. And then we have gated graph neural network. So they have used GRU to aggregate it. So in this case, they have used GRU at the outer layer. You can see here. This one is the self. This one is the attention part, and over it they use GRU to update the value. So you can see here, this is a very good article. You can take the reference. It's available on RQ. You can see here two options. So these are the various methods like ChabNet, the aggregation method, and the updater method. So they have played a role here. Like graph attention, so they have used aggregation as a graph part, graph attention part here. They have used the updater like this. Okay, here in tree LSTM, so they have used LSTM in the updater part, and the aggregator part is different one. So there are various combinations, and that's how the people have developed GNN variants. Okay, so how it's working, how we detect it, what is happening here. We know that these values are known to us. Known to us means, now take it, now this problem you can solve it two different ways. Okay, let's take it a classical way. Classical way, I have some data. So this one is one data, feature 1, feature 2, feature 3, and the label is there that it is not a fraud. Then another data, this one, feature 1, feature 2, feature 3, label is not fraud. The another data, feature 1, feature 2, feature 3, label is a fraud. So these are data which are available. And then a new feature comes, feature 1, feature 2, feature 3, and the question is whether it's a fraud or not. It's a simple classification problem which you can solve it by any classification approach, from simple machine learning to neural network or complex classifiers, because we have labeled data. So what we do usually is we train the data on the known features, and then we test it and test it on the new unknown data, and then try to find out what is the answer. The same problem you can solve it by graphical networks. And now the graphical network is there. Okay, so we have this data, we have another data, their interconnection is known to us. Okay, and we want to find it out that what is this. If this is value, So then is it a fraud or not a fraud? Okay, we will solve it. We will solve it mathematically in the coming slide. That is basically, this slide is just to show you that how the same problem can be done two different ways. But in earlier case, we are not talking about the relations. Straightforwardly, we are taking the data and trying to solve it. But here, we are putting some relations are also there, some connections are there. Well, that will help us in increasing the efficiency of our models there. We already discussed the representation of a graph, okay, networks and data there. Concept we have discussed. We have talked about CNN earlier, okay. So I'm just, this is CNN which we have discussed. Okay, we talk about now mathematics, how it will work. So if this is the representation, if this is a graph which is given to me, so then how I'll do it mathematically. So this is basically, I develop first a adjacency matrix. That means which node is connected to which node. Okay. So you can say one self is not considered here. So one is connected with 2, 3, 4. So you can see one is connected to 3 and 4. If there is a connection, we make it 1. If there is no connection, we make it 0. If it is directed, then it's going out, we take as positive 1, and coming in, we take a negative 1, and likewise. Since it is not directed, we are taking 1 and 0. So you can see, now if I know this matrix A, that means I know this graph. That is how we do it. Then we go to the second part, and that is basically we develop a degree matrix. Degree matrix means what is the strength of the connection, how this node is connected to how many different nodes. So we can see here one is connected to 1, 2, 3. So you can see it is 3. So one has a strength of 3. And other way of doing it, you just take the sum of rows or sum of column. So 1, 2, 3, and then 2, and then it is 2, then it is 2, and then it is 1. So we have 3, 2, 2, 1. This is basically how we represent the degree. So degree represents the strength of that particular node. Okay, and that is either sum of, you can take sum of columns or sum of rows. It will work, but or you can check it from your. So good is just you find out the adjacency matrix. From there you can easily calculate what is your degree matrix. Then we have feature matrix. So what is my feature matrix here? And the feature matrix here is this one. So one means this node, it has 3 features: 0.2, 0.1, 0.5. Similarly, node 2 has 3 features, node 3 has 3 features, node 4 has 3 features, node 5 has 3 features. So this is a feature matrix. Okay, so these are the features here, and we represent it by X. Okay, and then what we will do, the next step, we multiply the adjacency matrix with the feature matrix. Well, this is something very interesting. So what we are doing, you now just understand it. We are multiplying this row with this column. Okay, so what we are doing is we are just multiplying here, and then if you go for multiplication, matrix multiplication, it is nothing but it's summing the features. That is exactly what we do, the aggregation part there. So it is what we are doing is 1 into 1, we take the multiplication and take the sum. That is the impact here. That is basically impact of the features for node 1. Okay, then we go for this second, we go for the third one. Okay, and that's how we create this A into X. Then we take the for A for first, then we go for the impact of the second feature, we put it here, and then we go for the impact of the third feature, we put it here. That is how the first node impacts we have calculated. That is the impact of other nodes. Okay, because adjacency will give idea about other nodes. Please note here, in this adjacency matrix, the individual is not counted here. So it is basically an aggregation, because you are multiplying one by something and then adding it up. It's a one form of aggregation. I'm taking a simplest example here. You can use other methods also for aggregation part. Okay. So this one is what we have done is, and then what we do is we modify it, adjacency matrix. We add an identity matrix to it. That means the self part is connected here now. We call it modified identity matrix because the self part is connected. If you connected the self part, your degree will change, obviously, because now you are considering your own also. And then we take an inverse of it. Okay, it will help us in calculating few more things there. I will show you basically why we are taking inverse of this degree matrix, because at the end we are looking for calculating the mean value. So it's we have to divide it by the that part, so that comes automatically from this matrix here. So we have new adjacency matrix, we have feature matrix, we multiply these two, okay, that we write it here, and then we multiply it by D inverse. So it will give me the everything, the mean value of everything. Okay, what is the mean here? Mean is basically this product divided by the number of participants. Okay, so that's why I'm using D inverse. I'm using a simple operator, that is mean, for update my whole calculation. Okay, I go back to the slides. I'll show you where I'm doing it. So I'm using the mean here. Also, I'm using mean here. So I'm just taking the mean of everybody. Okay, so mean of everything is the sum divided by the number of participants. So that's how I modified it here. You can see here, this one, if I multiply this one, so they are just summed up, and if I divide it by D inverse, it's a mean value of that. So that's how I calculate this matrix. Okay, so this one is basically what we have done it. And this is people talk about various mathematicians, they come into it to see the effects, because we know D inverse. You all are mathematical people. What is the impact of multiplying D inverse with that one? Or if I do a transformation D half minus half and do a pre and post, so what is the impact of doing this one? Okay, I leave that it for you for your analysis, but this is now my modified A. So modified A is nothing but D inverse A, which is transformed like this. So now I have complete formulation. Now let's understand how the weight updation or learning take place. Very simple one. You can see these are the because in this process which we have discussed so far, there is no learning. Okay, so how the learning take place, and here it is basically. So we have learnable weights. So we have first layer. So we have initial weights, we have feature matrix, and we have first layer, and we do this operation. We apply ReLU over it, okay, to kill the negative part. You can take the activation function, so you can take its activation function. Then again you multiply it by weights and multiply it by your A. Then you again apply soft max over it, and finally you have Z max matrix value. Okay, so this is how this whole setup will work, and once it stabilizes, then whole network will learn, and when you pass a new data to it, then you will have an answer for those things there. Okay, so that is how it will work. And now there are various things you can do it. So I'll take one of the case study to discuss, and then if you have any query, I'll take your questions then. Okay, moving further. Just 1 second. Oh, okay. Just 1 second. Yeah. Okay, so this is a case I'm going to discuss what is SCMG based human activity recognition. So the job is we have SCMG signals, and we have to identify what is the activity a person is doing basically. So we have data acquisition. A setup is there. You put sensors on the muscles, and from there different muscles you can get a different signals. Okay, and then you apply a denoising, because when you collect the data from the muscles, there are noises because they are very sensitive, and there are noises because of interference, electrical signal interference. There may be there are issues or noise because of intermuscle activities and all that. And then you apply feature processing. Okay, so we have certain features about those things there, and then we create a graph neural network, and then we use this graph neural network to classify these what are the activities which are being done. So this one is a wavelet theory we applied for denoising, not agenda important here. And then we use these as features, like 11 features out of it. From every signal, we calculate MAV or root mean square or zero crossing and likewise. And from there, then we try to find out try to develop a graph there. So this is a graph. So we have here, we have taken 500 edges there. So the question is how to build a graph. And to build this graph, we have used Pearson correlation coefficient approach. So we have different points there, and then connection between the points. We use Pearson correlation. We put a threshold. If value is more than that value, there is a connection. If the value is less than that threshold, there is no connection, and that's how we have generated a graph from there. And then we have these graphs for different scenarios, and then we go for a graph matching. So if the two graphs they match each other, then we can say, okay, this is the activity. This is one way of doing the things. This is what we have proposed. And then we checked it on the performance matrices, and we found that we take two cases, a normal case and then a person who is abnormal. These are the 10 subjects being taken here. And then you can see here in some subjects the accuracy level is very high, but even if you go for the mean of the predictions, it is very good accuracy around 98%, and in abnormal it is a bit high because it is clearly identifiable. You can clearly see that okay, there is something happening there. So the accuracy level is a bit more, and this is one application. And then we compare it with various other methods are there, like SVC or KNN or MLP and then GNN, and we found that GNN performs better than most of the other algorithms which are available in predicting the various activities. So, and these are subject wise, and this one is the mean of the all calculations there. So this is how just to prove that how good is this algorithm or this approach for this type of applications if you compare with the different algorithms there. Okay. Okay, so this is all about um, this discussion. Let me check it if I have another part there, mathematicals, I would like to share with you. Just give me a second so that if I can find it out for you, I will show you that part also. I think I've done it, but I forget it, whether it's still with me or not. I prepared a very long back. Let me see if it is there, then I'll discuss one with the use that one. This is the same one. Just give me a second so that I can check it for you. I think where I put it, that example, if it is there. Yeah, so one thing which is important, let's take it from here. Two things which is not there. So understand it. This is this thing you have this node and the connection. So you know X and A, and then what we are talking about is basically we represent it as a H and A. H are the features and the adjacency matrix. Okay, so that's a conversion in H and N form, and then if I try to find out what is this node, how it, whether this node is good or not, or it's a bad node, or what are the impact, because this is the new point which is appearing. That is basically a node classification. Okay, and then if I try to find out each and everything here, let me take a each and everything here. So that means structure completely I'm taking it for my consideration. That is known as a graph classification. And if I am trying to find out the link between these two, what is the link between these two? That is basically the link prediction. So these are the three common things which usually people do when they do it for your GN and graph neural network. Node classifications, graph classifications, and link predictions. Okay, and let me see if the example is here. Okay, this we already discussed. Okay, this we have already discussed. We already discussed this part also, feature matrix and the calculations. Okay, we have talked about the weight updates. This we have discussed. Yeah. Okay, so yeah, that's all from my side on graph neural network. If you have any questions, please unmute or like in chat box. I'll happy to answer your